Then I guess we can start. Today we're going to learn about place capability graphs, and the speaker is Zach. Take it away.
Okay. Yeah, thanks for the introduction. I'd also like to mention that this is joint work between collaborators at UBC, ETH Zurich, and New York University. So I gave a version of this talk at UPSLA earlier this year that was 12 minutes. This one's going to be, I think, about like 45 to 50 minutes of like actual content. So there's a bit more time and we can go into the technical details, which, yeah, I'm kind of excited to do. So to start, I guess I'll make a statement that I think probably a lot of people here agree with, which is that Rust's type system is special. And one of the things that makes it special is that it tracks this notion of ownership. So in Rust, values are owned by places. Assignments can be seen as transferring this ownership from one place to another. And by default, values can only be directly accessed via the places that own them. But if you were to program kind of exclusively in this style, it would be quite restrictive. So Rust has a feature called borrowing that allows this ownership to be temporarily transferred from one place to another. And this borrowing is also tracked by the type system. So when a place is borrowed, for example, the type system restricts on how it can be used. So these features of Rust type system make it more restrictive compared to other mainstream programming languages. So compared to, say, C or C++, Rust accepts fewer kinds of programs. But as a community, we're willing to abide by these restrictions in order to take advantage of the various guarantees that the Rust type system provides us. So perhaps most famously, Rust guarantees that if the compiler accepts the program, then the compiled program will be memory safe. And I put this for free bit in quotes because if you're, say, a novice Rust user, you might feel like fighting against the borrow checker to get these properties doesn't really feel like you're getting anything for free. But the point is that if it compiles, you don't need to worry about it. But there is another quite important benefit that's a little bit less obvious, which is that these guarantees also enable us to reason about Rust code in some powerful ways. So in particular, the type system facilitates this idea of modular reasoning, where you can show properties about a program just by looking at the individual functions. So if you take a function like this, you can sort of tell just by looking at it that this assertion will always pass, regardless of how f is called or if there's concurrency or whatever. And the reason we know this is that the type system will guarantee, amongst other things, that different references or references to different pieces of memory will be passed in to f, so x and y will not alias. So the second assignment cannot change the target of x, and it will retain its original value. And as like people in the community, we often reason informally about programs in this way. And if we want our analysis and verification tools to also do this kind of reasoning, those tools would require some model of Rust ownership and borrowing that would allow it to sort of make these kind of conclusions. Like this information is not sort of directly accessible from the compiler, for example. And the development of such a model is the focus of this work. So if you are building a Rust analysis tool, your tool will need some model of Rust's ownership and borrowing in order to sort of extract these guarantees. So your options are either to develop your own ad hoc model for the purpose of your verification tool, or to use some existing model that's already built. Now, if you tried the build it yourself approach, one of the issues you'd quickly run into is that Rust's borrowing is actually quite complicated. So your analysis might be concerned with where a particular borrow in the program expires. And what's challenging about this is that there's no sort of syntactic annotation indicating that where this borrow of x expires in the program. And in particular, this one looks a little bit tricky because the borrow certainly needs to expire before the assignment to x, but somehow still needs to borrow x possibly after the end of the if statement. And this program is accepted by Rust, and I think people with a certain amount of familiarity probably understand why it is that Rust accepts this program. But this is just like one particular example where modeling this borrowing is kind of challenging. There are other complicated features like two-phase borrows, interactions between like shared borrows and immutable borrows, borrows inside structs, etc. So if you wanted to model Rust's ownership and borrowing, you would essentially need to do much of the work that Rust's borrow checker is already doing. So then, if a better solution might be to take some existing general purpose model and incorporate it into your analysis tool. And the good news is that there are many models from prior work. I'm sorry if I did not list yours here. There's just way too many to list. But the bad news is that all of these models capture different aspects of the type system. So they all serve different use cases in general. So as the author of a verification tool, you need to decide which model your analysis tool should use. And so to answer this kind of question, I want to show some of the different properties that make these models useful for analysis and verification tools in general. So first, we would like many analysis and verification tools want to perform modular reasoning. So they want to take advantage of Rust type system guarantees when it comes to modularity. And to do so, you need to reason about the borrowing across function calls and loops, because this cannot be done statically in a modular fashion while you retain precision. So in particular, you can have functions that rebar from their inputs. You can have borrows created inside loops that are used after the loop. And we want to be able to reason about these kind of behaviors. So this requires sort of summarizing the possible behaviors of function calls and loops. And we would also like these summaries to be generated automatically, so not requiring user-written invariants, for example. A second aspect of models that can make them useful is having a close connection to the Rust compiler's internal representation. So this might seem like this is just an implementation detail, but I would argue that this is important for a much more fundamental reason, which is that Rust language does not have a formal semantics. So the closest thing we have to a formal semantics of Rust is what the Rust compiler decides to do. So if the model is closely connected to Rust's internal representation, like mirror or here, then you have sort of by default a close connection already. And there are also some more practical reasons for this. So if you're building a tool, your tool might also just want to operate on mirror anyways. And it'll be much easier if the what your tool is analyzing, the representation of the model, the representation of the Rust program, and sort of concepts that can be explained back to the user of the tool is all using the same representation. Because you don't need to translate between these different representations and potentially introduce areas where unsoundness could sneak in. And then finally, on a kind of separate note, we would like models to be able to reason not just about individual borrows, but also sets of borrows. So in Rust, you can define data structures like this one that can store multiple borrows. And these borrows inside these data structures are still tracked by the type system. So for example, here, even though the borrows in these three different fields of tree node all have the same lifetime, take A, the borrow checker will guarantee that they all point to distinct regions of memory. So the borrows in left and right won't intersect, for example. And we would like our models to be able to reflect these guarantees. And so prior to this work, there wasn't really any single model that could satisfy all three of these properties at the same time. So we developed our place capability graph model, which we'll call PCGs from now on, to meet these three criteria. So it achieves this goal of getting modular summaries and function calls and loops by extracting data from the borrow checker. So our analysis doesn't actually perform a fixed point analysis. It's actually quite straightforward, just looking at each program point once. And the way it computes these summaries is actually just by extracting it from Rust borrow checker facts. And it connects to Rust internal representation by operating on mirror. and capturing these notions of ownership and borrowing analogously to the compiler. In fact, some of the facts about ownership and borrowing are actually just extracted from the compiler itself. And our model is able to reason about not just individual borrows, but also these sets of borrows via a novel construct that is called lifetime projections. So now I'm going to introduce the model itself. So at this point, the talk will get, I think, a bit more technical. And so feel free to interrupt me to ask questions like during this portion, in case you're any confusion on the technical things that could help by like quick clarification. So our analysis takes in a function as input and computes this PCG data structure at each point inside the function. And so we call our data structure place capability graphs because it associates places with capabilities. And these capabilities describe what the compiler believes can be done on these places at a particular program point. Then nodes in the graph denote memory locations. So these can be either places or these lifetime projection nodes that I will introduce shortly. And edges in the graph denote the temporary transfer capability between locations. So for example, for borrows, etc. And technically, these edges are hyperedges, so they can connect not just single nodes on each side. Oh, okay, excellent. Yeah, so I was saying these edges are technically hyperedges. This is actually not it might sound confusing. It's actually not as confusing as it sounds. These can be thought of just as normal kind of graphs, basically. So the capabilities in our model, we define 3 of them: exclusive, read, or write. And again, these are associated with places. And there's also the possibility in the model for places to have no capability at all. So for nodes, again, as I mentioned, we have place nodes, lifetime projection nodes. The place nodes are just a pair of a place and a capability. So this top one denotes having exclusive capability to place P at a particular program point, which means that the compiler thinks it's okay to either read or write from P. And then it's also possible to have just read or just write. And then a place could have no permission if it was being borrowed. So if you create a mutable borrow to a place, that place becomes unusable so long as the borrow is live. Lifetime projection nodes are used to represent the borrows stored in a place under a particular lifetime. So these are quite important in our model because these are what allows our model to connect with information from the borrow checker. So in particular, if you're familiar with Polonius, Polonius has this notion of an origin, and these lifetime projection nodes are essentially analogous to Polonius origins. And these are introduced based on the types of places and their capabilities. So if P has a type like this, and we have exclusive capability to it, then in the PCG, there will also be lifetime projection nodes corresponding to the borrows stored in P under different lifetimes. And so these are actually like sets in the sense that either of these could contain no borrows. They could contain a single borrow. They could contain, for example, in this list, many different borrows. So that's sort of how this works. So I want to show how this notion of place capabilities evolves during the execution of a program. So what I'll show in this example is just the PCGs at the different intermediate stages of the analysis of main, but just only looking at this one node P. So not the full PCG, just looking at P. So at the end of the first statement, P has a value, so it can be either read from or written to. But then subsequently, when it is borrowed, P's capability gets downgraded from exclusive to read-only. So for as long as this borrow is live, you're not allowed to mutate P, but you can still read from it, for example, to create other shared borrows. But then at the end of the next statement, the borrow expires, so P regains its exclusive capability. Subsequently, the value of P is moved into R, so P loses the capability to read from it, but a new value can still be written in, so it still has this write capability, which is in the next statement, a value is written in, and it goes back to exclusive. So finally, for the borrows, because this variable s can read or write to the value originally in P, P has no capability so long as this borrow is live. And then at the end of the next statement, when the borrow expires, he gets its exclusive capability back. So are there any questions about this part or up to this point?
I have a quick one. So the
Yeah.
write capability is kind of used to do like a place that you must still initialize or something, right?
Yes. You don't necessarily need to initialize it, of course, but the capability to put a value in if you want to is, yeah, represented by the write capability.
So is that how you can have a place that is writable but not readable? Is if it's not initialized?
Exactly, yes.
Okay.
Or if
Cool,
you've
thanks.
moved a value out of it, like after moving out of P, putting the value in R is still a write only. Okay. So we're now at a point where we can introduce capability transfer. So we can look at actually the full PCG analysis of a function. So it starts at the beginning of the function having exclusive capability to both of the arguments, so P and S. And then because analysis is on mirror, the return value is actually put in this particular place we'll call return. That's write only for now, but then this return is actually an assignment that's going to put a value there. And the analysis starts just by going in, looking at each statement in order. And statements are sort of seen as these transfers of capabilities. So the analysis wants to transfer capability from the thing on the right-hand side to the left. So that is the place P'd up first, but you can see that P'd up first is not currently in the graph. So to obtain the capability, the analysis reorganizes the graph to make this place accessible. And the way it does that is by introducing what's called an unpack edge. And so that looks like this, where the capability from P is gone, and we now have capabilities to P dot first and P dot second. And this edge indicates where these capabilities came from. And so this is the PCG at this like intermediate state, like while the operands of the statement are still being evaluated. And so now after this reorganization, there is a place to get capability from. And so that values being moved out, P dot first becomes write only. And then for the left-hand side, because we're doing a new local variable declaration, the PCG introduces a node for temp with write only. And then because the value is being moved in, that gets upgraded to exclusive. So that gets us to this PCG at the end of statement 5. Now, between each statement, the PCG does another attempt at reorganization by trying to basically revert these temporary transfers. So these kind of, by looking at all these edges and seeing what capabilities can kind of flow back to where they came from. Now, in this case, nothing happens because these have different capabilities. There's nothing to restore P to, but we'll show later how this actually sometimes does have an effect. And this idea of sort of reorganizing to undo these edges becomes much more important when we get to borrowing. But anyways, moving on to the next statement. So this is, again, a transfer of capability. So capability from S is going to get moved out. It's already in the graph, so the analysis just downgrades it directly. And then P dot first, also still in the graph, that gets updated to exclusive capability. And now at this point, the reorganization between statements actually has an effect because both P dot first and P dot second have exclusive capability. That just gets sort of undone and P goes back to its original state. And then finally, there's the return statement, and this is just an assignment. So capability goes out of P and into the return place. So that kind of concludes this example. Any other questions at this point? Okay, great. I will move on to the next part. So if all there was ownership in REST, this would actually kind of suffice to explain most of the capability flow. But things get a bit more challenging when we get into borrowing. So we're going to look at this example, but before we do, I want to mention something kind of interesting about it. So here we have y as a borrow of x, and z is not a borrow of y itself, but rather a borrow of the target of y. So y and z are both aliasing x. Now it might seem like this is sort of breaking the REST rules because we have two mutable references to the same spot. But actually the rules are a little bit more nuanced. So intuitively, REST accepts this program because even though these are both aliases to the same spot, they're never live in a sense at the same time. And we'll show how this is explained in the PCG in terms of capabilities by noting that throughout the evolution, only one of X, star Z, and star Y will have a capability at any given time. So just to start the example, the first statement's quite straightforward. X is introduced into the graph with exclusive capability. Next statement is an assignment, so it's a transfer of capability. So the one on the right-hand side we want to remove is X, and because Y is going to be able to both read and write to X, its capability is removed completely. For the left-hand side, we introduce place node for Y, and then because Y stores a borrow, there's now a lifetime projection node for it. So again, as mentioned previously, this corresponds to what in Polonius would be the origin associated with Y. And this decay is just the whatever represents whatever lifetime Y has. And because this is Y is going to store a borrow of X, the PCG introduces a new type of edge called a borrow edge. So this quite literally corresponds to this borrow in REST. It's associated with this metadata. And in Polonius terms, this sort of represents the notion of an origin containing a loan. So you can think of it as kind of like visually representing that fact. At the next stage, there's then a reorganization step. So here, the PCG needs to determine if this edge should be moved, if the capability should be moved back into X. And the way it makes this determination is actually by querying the borrow checker. So what it queries the borrow checker is whether or not Y contains any borrows that are going to be used later. So this is, again, in Polonius terms, corresponds to the notion of an origin being live. And so to query this is just a simple query into just a set of borrow checker facts. Intuitively, we know that it is going to stay because Y is used in quite literally the next statement. But from the analysis perspective, this is just like a simple query that doesn't require looking ahead in the program. So nothing happens at this transition, and we move on to the next statement. So to generate the PCG at the next point, again, it's a transfer of capability. And here, what we want is the capability to star Y. That's not in the graph at this point. You can see we have Y, but not star Y. So to get this capability into the graph, the reorganization introduces a new edge called a deref edge that gets us star Y in the graph. And what this edge sort of indicates is that star Y is getting its capability from the borrows that were stored in this lifetime projection at this point in the program. And you'll notice another thing, which is that Y's write capability has been removed. Read capability has been removed. So you can't read Y since the borrows, in a sense, have been moved into star Y. You could actually still write into Y. So you could put a new value or a new borrow into Y. This is kind of a subtle point, but I could go over an example later if there's time. So anyways, now the graph is reorganized. We have star Y inside, and we can get its capability taken out of it. I guess at this point, maybe Xavier, if you wanted to ask your question.
Yeah, Um, could you explain to me when you would have multiple lifetime projections in one of the I guess deref edges, or like is there a situation where you would have a box that would have both like y and multiple different lifetime projections, or
No, it would only ever have one, only the
yeah.
outer lifetime projection. So if y had a stored was like a reference to a reference, the dref of y would only be from the outer lifetime projection.
That makes sense, but I mean, in your PCG, can you ever end up in a situation where this purple box would contain multiple different, like maybe one for Y, one for something like Z or something like that? Does that make sense?
So it makes sense. So not for this type of edge, because this
Okay.
edge is only for drefs. Now you can get edges that connect multiple lifetime projections. So if you like move from one place to another, and then this move ends up moving lots of borrows into different lifetimes, then you can have that. Like if you have lists
What
of
if, I don't want to take up too much more time, but what if you had like
Mhm.
an if statement, and then that statement returned either Y or something else, and then you did the deref after
we will get to
of
that.
the
There's
result
an
of that
example
if
that shows
expression?
this. Yes.
Yeah. Okay.
Well, R.
Yeah, sorry, I'm Ralph. Sorry, I just didn't set
Oh,
the username. Hi. So what is the permission on star Y here?
so when it's in this intermediate state, it has exclusive, but because it's going to be reborrowed, it goes away. So
Okay,
what
but
happens
exclusive.
subsequent?
So
Mhm.
previously exclusive meant you could move out from it, which you can't do with a mutable reference.
No, sorry. This is actually unrelated to being able to move out. So exclusive means to read or write
Okay, so
in
so
this model.
previously
Yeah.
you did these reads where the reads were moves, right? And the E changed to a W. So that I couldn't do this here on the
Mhm.
star Y.
Yes. So the ability to move out is not explicitly represented in the model. Basically, I mean, you can tell from the type signature whether or not something can be moved out from. And we do actually represent, like, understand this notion. Sort of, there's a distinction between places that are owned, like X, and places that are borrowed, that derive from borrowed places, like star Y. There is a distinction that's made, but in terms of the capabilities, it's not really present in the capabilities.
Okay,
Does that?
thanks.
Yeah. Okay. Yeah. So I'll sort of move on with this example. So the next thing with star Z is kind of similar to what we've seen before, but at this point, the reorganization has a bigger effect. So any derefs edges can always be sort of packed back up. We can always undo that. And then it is at this point where Z's um, lifetime projection is no longer live. So this is, again, in Polonius terms, something that you can just query from the borrow checker. So then this borrow edge is removed. Z, as a side effect of this, loses its read capability, because if Z is not storing any live borrows, there's no sense in which it can be read. It's not going to be used later on anyways. And then the reorganization continues until this point, and this edge cannot be removed because the borrow checker says that this lifetime projection is still live at this point. And then the rest of this kind of goes accordingly to what's seen before. The reorg after the last statement puts capability back into X. And so we'll see, as we've seen, basically at any point, either X, star Y, or star Z has exclusive capability at any given point. It's never the case where you have both of any of these having capability at the same time. So in this next bit, I'm going to go over back to this example, and this will soon answer Xavier's question about the conditional borrow thing. So as I mentioned before, we want our models to be able to answer these kind of questions about borrow expiry. And this one is kind of tricky because it seems like you have a borrow that expires, but then is still subsequently needs to be live later in the program. So the answer to this is that actually the borrow expires at 2 different points. It expires here, but then also after the last statement. And I'll show now how the PCG represents this, and also how the PCG more generally indicates where it is that star R2 is getting its capability from. And to do so, I'm actually going to switch into the actual PCG results that you get if you were to apply the PCG to this function. So what we have here is a visualization of the actual results computed by the PCG. So up top here, we have the code example. This bottom graph here, although you probably can't see it very well, is the mirror. So this is what the PCG actually operates on. It's a control flow graph representation of the program. The first mirror statement is highlighted, and this is the PCG at that point. So we can see that when the borrow is created, the PCG adds this borrow edge. And as I mentioned, it actually corresponds to a rest borrow. So we annotate it with borrow 0 here. And then this question mark 6 is just like whatever the compiler decided to name the lifetime of R1. So if we look into the branch where the true branch where we enter the if statement, we can see that borrow is still in the graph. And the reborrow gets put, then this R1 is reborrowed into R2. So that's a separate borrow. And this visualization is a little bit different from the slides in that we can't actually represent hypergraphs. So some things that were like this DRF edge is actually looks like two edges. Hopefully that isn't too confusing. But another just point I wanted to mention is that this gray line here indicates a direct alias relationship. So this is not a transfer of capability, but just based on the metadata we have, knowing that this is a borrow, we know that X is a precise alias of star R1. So anyways, this is what the borrowing looks like on the if side. Now let's look at the else side. So as soon as the branch is entered, that borrow is no longer there. So we're in a state that looks like this, and then the borrow just seems to have disappeared, which is correct. Like the borrow needs to expire. And the PCG actually explains how this happens. So our analysis, in addition to generating these graphs, it generates the intermediate states and indicates why it took these various actions. So the first thing it did from the initial state that got inherited from the initial basic block is to remove this borrow edge, because the borrow checker has reported that this lifetime projection is dead at this point. And then if we go to sort of the end, it creates these new borrows and reborrows for some reason into R2. So at the end of this, I'll make this bigger so we can see it. So we have one state of borrowing at the end of the else and one state of borrowing at the end of the if, and these need to be merged together in a consistent state at the end. And this merging corresponds to basically what the borrow checker does as well, which is that it just adds the edges from both sides. So we have that borrow still being alive at the join, but now it's only alive conditionally. So it's probably hard to see, but this borrow in the PCG is associated with path-sensitive information, indicating the circumstances under which the borrow is live based on the control flow. So in particular, if you go from block 0 to block 1, this borrow is live, otherwise it's not. And same thing for Y. So what we have then at the point of the DREF is an explanation for where R2 is getting its capability from. So star R2 is borrowing from either X or Y, depending on the control flow. And you can see these gray edges indicating it's actually a direct alias of one of these two locations. Okay. Are there any questions at this point? Also, Xavier, I'm not sure if this answered your question from earlier.
It did. Thank you.
Okay, great. In this case, I'll just continue since we're just for the sake of time. Okay, so we've shown how the PCG handles direct straight line code where you don't need to do any summarization. Of course, I mentioned that the tricky thing is actually summarizing this behavior modularly. So for function calls, the challenge is reborrowing. Now, so if you have something like choose, it can reborrow from one of its inputs. And so the way this is handled in the PCG, oh yes, and clients don't deal with the actual implementation of choose. They can only look at the type signature. And to handle this case, what the PCG does is it constructs a shape of the function from the type signature. And the shape always takes the form of a bipartite graph from the inputs to the outputs. And then at the function call itself, this shape is just substituted into the graph. So what the shape tells us, like from the type signature of choose, is that the result is going to borrow from either one of its inputs. And then there's just a simple substitution. So we know from the client side that R is going to potentially borrow from either X or Y, but not precisely how this occurs. And we have a similar situation with loops. Again, you can have these borrows created inside the loop that survive beyond them. So this function will return a reference to the last element of a loop. And to summarize such borrowing, we need to get a shape for this. So we need some shape that's going to work for the entry point of the loop. And that can also, regardless of how many iterations, and also be applicable at the end. And I won't go into too much detail how this is done, but we also just get this by the borrow checker, querying the borrow checker for what borrows could be blocking stuff at the loop head. So the shape is constructed not by looking at the loop at all, basically, just by querying the borrow checker before even considering the loop. Ralph?
Yes, thanks. So you said earlier bipartite graph from the inputs to the outputs, but there's only one output, I would think, which is the return type. So like how can there be multiple outputs?
Okay, that's a great question. So there's two ways. The simple way is that you could imagine this could be a pair of borrows. So in which case you would have two, or like a list of borrows or certain struct containing multiple lifetime parameters. Does that?
Okay, so pair is just one example of a type. So it's the number of lifetime parameters in the return type. Is that the way to think about it?
Yes, except there's a caveat that I'll get to in about 3 minutes. Like there's another case that I'll explain in 3 minutes. Yeah.
Okay, cool. Thanks. I have
Okay.
I have some inklings what it might be, but I won't ask now.
Okay. Yeah, so this is the shape for this loop. Loops can have more complicated shapes. So unlike functions, loops are not just limited to bipartite graphs. So you can have like reborrowing inside of a loop to create a fancy shape. So now we can actually talk about the example why functions can actually have different bipartite graphs. And this is nested references. So what I mean by nested references are references to references. So you have like R1 and R2 are both references to two integers. Now, if you look at this function main, you might think that this assertion should always pass. The reasoning being that R1 is a reference to X, and then you set R1 to 0 here, X should be 0. But actually, this isn't necessarily the case. And the reason for this is G. Because what G could do is it could swap the borrows stored in R1 and R2. That is the borrows under lifetime A. So the effect of G could be to put the borrow of Y into R1 and put the borrow of X into R2. Now, to handle this case then, we need to sort of do something. Oh, sorry, I skipped ahead. We need to do something to represent the borrows that are going to be stored in R1 after the borrow of R1 expires, since R1 has the capability to change what R1 points to. And so to do that, we introduce this notion of future nodes, future lifetime projections, rather. So basically, the way it works is there's another edge added to what R1 is going to have once it becomes accessible again. So basically at line 11 here, whatever borrows end up getting put into R1 and R2 will become accessible via R1 and R2 when the borrow of R1 and R2 expires. Yeah, sorry, it's kind of a mouthful, but hopefully this kind of gets the gist across. Now, we also need to do something else for functions because, yeah, based on this idea of inputs and outputs, it seems like there's no shape for G because G doesn't have any outputs. But there's a sense in which it does have outputs. And the sense in which it does is that there's a version, or there's a set of borrows under this A lifetime for R1 and R2 before, and a set after the call. And these sets of borrows are going to be different, potentially. And what you can use to sort of express this shape is this sort of like crisscrossy thing that represents, you can move the inner borrows between R1 and R2. So one way to have output nodes is for it to be an actual output of the function itself, but then we can have these sort of like implicit outputs based on the nested references. So are there any questions at this point? Okay, cool. And then just one final note is that after the call, R1 does become available again. And this is handled just quite easily by just removing the future labels. So once R1 and R2 expires, R1 and R2 are accessible. So we no longer consider them the future borrows in there, just the borrows that are in there now. Okay, so that concludes the sort of technical meat portion. I want to talk just briefly about the evaluation. Kind of relatively quickly. I'll leave still a few more minutes for questions at the end. I just want to highlight a couple of things that we looked at. So we wanted to see how much REST code we could support, whether or not our models are actually capturing the right thing, and how easy it is to integrate them into tools. So for the first part, we just took an approach where we looked at 500 crates on crates.io and tried to run our analysis on everything. And the results were actually quite good in terms of what we could construct models for. There were about 2% of functions that our analysis didn't handle, and then most of that is stuff that we don't really set out to handle anyways. This would be like raw pointers, inline assembly, and other parts of unsafe REST. And then there's a kind of very small number of engineering-related issues that we think are possible to fix in theory. But of course, just because we can create these models doesn't mean they're necessarily correct in any sense. So we want to make sure that if the PCG says, for example, we don't have capability to replace, that this is what the compiler actually believes. So the way we evaluated this was using a mutation testing approach, where we would take a function from our big corpus of REST functions, generate a PCG at some intermediate point, and then see what places don't have capability. So here we have vec being blocked by this borrow. So we should not be allowed to use vec at this point. So we would then create a mutant program that does precisely the thing that we think we should not be able to do, and send this to REST and confirm that REST compiler actually rejects it. And so this worked. We were able to run this to create 7 million mutant functions, and like almost all of them were rejected as we expected. Now, there was a very small number that the compiler actually accepted. And at a high level, the reason for this is that our analysis, this mutation testing, was not on source rest. It was on mirror. So according to my understanding, the reason why the compiler rejected these is because some of the borrow checking logic is done at the source level. And we kind of confirmed this also by trying to take these cases where the compiler disagreed with the PCG and actually write the corresponding surface rest program. And when we did that, the compiler would always reject it. So in practice, even these mutants that we did not, live mutants, don't actually, were sort of false positives in the fact that we couldn't replicate them. Finally, I want to just talk briefly about what it's like to integrate PCG into real tools. So the motivation for this work is Prusti, which is another project that we're working on. So Prusti is a verifier for REST. It encodes REST programs into separation logic and then does verification on that. And this creation of a separation logic proof was previously done via a lot of like ad hoc code. And this could handle sort of simple borrowing cases, but kind of didn't work for more complicated ones, such as borrowing in loops and sort of more advanced reborrowing across functions. So we updated Prusti to instead get the annotations generated by the PCG corresponding to what actions it took, and then translating those into separation logic proof statements. So this becomes just simply just reading off a bunch of, reading off this list from the PCG and doing this like one-to-one translation. So it simplified the Prusti code base a bit and let us support quite a few new features in terms of what borrowing patterns we could support. Besides this, we looked at a totally different tool, Flowistry. So this is the information flow analysis tool for REST programs. And Will Crichton, the creator, had recommended this to us because he mentioned that inside Flowistry has this alias analysis ad hoc implementation. And so as I showed previously, the PCG can be used to identify aliases amongst different locations. So we created a fork of Flowistry to do that instead. So we ripped out its alias analysis and instead have it query PCG. And as a proof of concept, this was a success. So it passed the test suite. And I want to mention just for both of these, this was actually quite a straightforward implementation. So both of these tools, like many other REST analysis tools, they operate on mirror and use the same mirror concepts as the REST compiler and our model. So things like identifying aliases, for example, is a very simple API about involving like REST places. So it's basically just like one single API call to integrate with the PCG. All right. So to conclude, I mentioned earlier that these models of REST ownership and borrowing are necessary for analysis tools. That there's sort of a gap previously in the space of models for the purpose of verification and analysis tools based on these three different criteria. I introduced the PCG model and talked a bit about some of our real-world experience and evaluation. If you want to use PCG, it's available. The web UI I showed earlier, where you can visualize the results, you can find that just from our GitHub link. You can also like write your own REST functions and visualize the results of that too, if you like. You could also reach out to us on Zulip. And yeah, if there are any further questions, happy to take them now.
Thank you so much for giving this talk.
Sure.
I'm sure there are questions. Sorry.
Yeah, if there are no questions, I also have more. I could also talk about future work. So
if anybody has a question right now, they can ask it. If not, we can hear the future work.
Okay, sure. So I mean, this is just like an
Anyway, I
Oh, sorry,
guess
Xavier and Ralph? Yes.
I think Ralph went before me, so Ralph, go
Okay.
ahead.
I already had more. Go ahead.
all right. Then I guess we'll to switch to work.
Okay. To avoid getting deadlocked, I was wondering, can you compare the expressivity of the PCGs with tools like Aeneas or Crusoe? Like, what does the PCG allow analyzing programs that those tools can't, or different programs, or?
Yeah, so I think in particular, this loop bit is probably different. So our analysis of loops is not a fixed point analysis. So we can construct shapes automatically based on the borrow checker info. I'm not exactly sure the extent to which Aeneas is actually successful in generating these shapes automatically. Another thing, so yeah, that's for Aeneas. Another thing for Aeneas in terms of the function calls is I don't think they handle this case. I mean, certainly I think in the implementation, the last time I checked, they didn't really handle nested references or references inside of structs, just from like an implementation perspective. It's a little bit less clear to me that they can handle this case. Like from what I've read in the papers, it wasn't clear to me that they can handle how like borrowing changes across function calls. In comparison to Crusoe, unfortunately, off the top of my head, I don't quite know. But we could, of course, discuss it later, since I imagine you are quite knowledgeable about what Crusoe is capable of. Ralph?
Thanks.
Yeah, thanks for the talk. This looks very cool. I'm looking forward to understanding better how it relates to all the other ways we have of thinking about Rust borrows. One thing that confused me a bit is you said from the like in terms of when you tried this on real world code and it didn't work on all the code you tried it on, you said something about raw pointers, which
Yes.
so I mean the borrow checker accepts that code with raw pointers just fine. And I thought what you're doing is kind of mirroring what the borrow checker does, but in a different way, and it's something that's more abstract in principle than just a pile of implementation. So why would raw pointers do anything at all?
Yes, this is a great question. So, in fact, in the general case, they don't. The part where it gets a bit tricky is this notion of a lifetime projection representing the borrow stored in a place. So, if you have a raw pointer to something that inside of it contains rest borrows, then what you'll have is the ability to copy the raw pointer, but that should not give you the capability, that should not duplicate the capability you have to the borrowed data that is tracked by the borrow checker underneath the raw pointer. Does that make sense? Like,
so we're talking like a star mute ampersand tick a
yes,
or star
exactly.
mute ampersand mute something situation.
Yes.
And so just to make sure I understand, so the problem is not that you are unable to prove this code safe, because obviously, I mean, so far you didn't make any claim that this proves safety of anything anyway, but you're kind of representing borrow checker information in a different way. It's that the borrow checker does something there which you currently can't represent.
I think that's basically correct. Yeah. The other thing is, we want to at some point have some like more semantic explanation for what a lifetime projection represents, and this is sort of, I think, relatively easy to explain kind of informally when we don't worry about lifetimes being inside of raw pointers. When you have the case with lifetimes in raw pointers, what that is actually supposed to mean in terms of the model is not quite clear to me yet.
Interesting question. I guess we'll have to follow.
Yeah, but this is definitely something I want to look at in future work.
Okay. Okay, cool. And then the other point, maybe quickly. So you said something about sometimes your mutated code doesn't get rejected. So the borrow checking happens entirely on mirror. So I'm wondering what that is happening on the surface here that you ran into. Is it
Yes.
like move checking? But I think the borrow checker also does move checking.
No, it's not move checking. So I believe there's some part at the translation from here to mirror, where the compiler can reject a program for a reason related to borrows. So I actually
Interesting.
didn't do that part of the evaluation, but I think there is like a comment in the paper, like there's a footnote somewhere that might explain this.
Okay, I will go look for that because I'm curious now. Okay, thanks.
Yeah, cool. Xavier?
Yeah, I had another question brought on, I think, by Ralph's question, which is
Mhm.
how do you go about like handling things like functions on Vec? Because I imagine that you can't like your PCG can't model those, right? Because you're doing like unsafe pointer arithmetic right there. But like for example, sorry, to make it short, like something like index mute on Vec, right?
Mhm.
That would be rejected by the PCG analysis, right?
No. So I think one reason is that because it's modular and that function does not have any raw pointers, there's no issue there. But I think there is one sense in which it might seem like there's an issue, which is that Vec internally does have a raw pointer.
Yeah.
And so like the question is like, how are we representing that type? And actually, so the unsupported raw pointer thing is a little bit of a lie in which we can allow for raw pointers just to exist. It's handling their explicit dereferences that are tricky.
Yeah, but I mean, somewhere in essence, in like the index mute implementation of Vec, you should have like some sort of pointer arithmetic and then conversion into a borrow, right? Like, I mean, unless I'm completely mistaken on
Yeah.
bulleted, but
right. So that's like an internal, like if we were trying to use the PCG on the Vec implementation, then we would probably not be able to support the code that actually, yes, exactly.
Okay.
But of course, clients of Vec are fine. Yeah.
Okay, yeah. So the question my sort of follow up there is how do you calculate the summary? Like you had that lifetime summary, where you had like your input and output lifetimes. I guess for index mute is probably trivial and there's probably only one way you can connect it, but like can you calculate that purely from I might have missed this. Can you calculate that purely from the signature of the function? Or
yes.
do you actually Okay. Okay. Thanks.
Cool. All right, I think we're at time. Unless there are any further questions. I could go over future work if people want to go over time.
Can you tell me who did that evaluation that you mentioned, the mutation
yes.
thing?
Jasper here, who is a co-author on the paper. Yes.
Okay, cool. Thanks.
We started 2 minutes late, so if you can fit the future work into 2 minutes.
Sure. I think I can just give a quick taste. So actually, future point is related to raw pointers. And this might seem impossible. Like, how could we do this? The type system doesn't restrict aliasing. There's no type system level capabilities. Okay, yes, but if you think about sort of code where you could do something really bad with raw pointers, like this one, where you use a mutable reference to y to modify x, actually this is UB. And the reason this is UB, I'll explain fast, is this notion of provenance. Actually, Ralph has very good posts on provenance, so if you want to actually understand what it is, read his blog posts. But basically, what if we took this notion of provenance and kind of used it in our analysis? So maybe not, and to be fair, maybe not the PCG analysis. Maybe this is better, like has something on top of the PCG that's separate. But if we were to do that, and we considered sort of like in terms of allocations, which are related to provenance, we could maybe reason about this modularly and say that, okay, either this pointer writes to y, and then this assertion is for a different allocation. So this should always pass if there's no UB. So if it's the case that int pointer isn't doing something crazy, then we should be okay. So if we wanted to extend the reasoning in this way, we'd also have to rule out UB. Maybe we could do some sort of thing where we propagate kind of constraints, figure out what conditions are necessary to exclude it. And besides provenance, there's also this other thing you might have heard of called tree borrows. So tree borrows is is a little bit different. It's like not a static analysis, it's dynamic. But there is, I think, some kind of sense in which you could take this like capability view on tree borrows. And maybe there's a way to kind of integrate the restrictions that are sort of described in tree borrows with what we have in the PCG already and the provenance info to get more expressivity around raw pointers. So that's some potential future work that I might be interested. I'm not sure, maybe it's a dead end, but happy to talk more about it. You can also just ping me on Zulip or whatever. Oh, and thank you all for your time.
Yeah, I would say let's all thank Zack again. And then I guess it's also my honor to already announce that we'll have another Rust for Memphis interest group meeting pretty soon, because the next one is mid-December, because end of December is when you're all on holiday, hopefully. Yes, in 3 weeks, we're gonna have what's the name? We're gonna have Opal, a student of Sasha. She was here earlier, but I think she left already. Anyways, so I guess see you all in 3 weeks, and bye bye.